volt or something. Let's see. Okay, so yeah, so gallium arsenide has a band gap of 1.43 electron volt. So that also you will see that when you calculate the wavelength corresponding to that, it will come out to be in the infrared region. So now what can be the use of LED which is emitting light in the infrared region? So even LEDs which are emitting light in the infrared region, they can be also useful. For example, as I've written here, you can see they can be used in security applications, industrial processing, as I've shown in counting number of items on a conveyor belt in a previous lecture on photo. Information is optically sent and received. So a photo detector will receive a light signal coming from a LED. So that is
Sir, your voice is not coming, sir. Sir, your voice is not coming, sir.
okay. So there was a break in my connection. So now can you hear me?
Ji, sir.
Yes, sir.
Okay. So till which portion did you follow? So before this, before I started about visible light wavelength range, have you followed what I have said?
No, sir. Gallium arsenide.
No, sir.
Okay, so gallium arsenide, I told you it's 1.43 electron volts, so it is in the infrared region. So I told you about the use of infrared LEDs. So did you follow that?
Sir, can you start? We
Yeah,
are
what
not
are you saying?
we are not getting, sir, all the things.
So you want me to repeat that part?
Yes, sir.
Yeah, so I was saying that what can be the use of infrared LEDs? So they cannot be used for illumination in that sense, but they can be used in other applications like security applications, safety devices. Then you have industrial processing. Like I told you about when I was talking about photodetectors, I told you about conveyor belts where you can count the number of items moving on the conveyor belt using a photodetector. So there, of course, you can use a LED photodetector and infrared photodetector and an infrared LED. And similarly, you have optical couplers, meaning there is exchange of information using light. For example, your source is a LED, which can be an infrared LED, and your photodetector will be also an infrared photodetector. So basically, the light signal from the infrared LED will be detected by your photodetector, and so this unit together will be an optical coupler. So basically it couples two things using light. And then you have remote controls in your homes, which also use infrared LEDs. Okay, so next I was talking about visible light.
Sir,
Hmm.
sir, about this direct band gap, indirect band gap, I have a little bit doubts. Sir, when non-radiative thing will become, that will be indirect band gap.
Yes, yeah. If it is not emitting a photon after recombination, it is emitting light. It is emitting energy as heat energy. Then it will be a that is the case of indirect band gap.
Sir, actually, I am using in project work, that is the perovskite material. Perovskite material is the direct band gap, but in some time that will be showing in like a non-radiative cases. It means that is the we will understand that is the indirect band gap or direct band gap, sir.
Okay, so that I am not sure. Maybe I'll have to look actually if there are other reasons why a direct band gap semiconductor might not give you large yield of photons when recombination is happening. There can be other reasons. So indirect band gap is maybe not the only reason. So there may be other reasons, but I am not sure about that.
Okay, sir.
Okay, so this visible light has this wavelength between 400 to 750 nanometers, and if you convert it into frequency, that will come to around 400 to 750 terahertz. So that is what I have written here. So how will you convert wavelength into frequency? Do you know? Okay, so it's yeah, so you can convert 400 nanometers. So which will do you think 400 nanometers give? Which of these two limits, 400 or 750? So the lower limit in the wavelength will give you the upper limit or the lower limit in frequency?
Sir, can you ask?
Upper limit, sir.
Yeah, so 750 terahertz will correspond to 400 nanometers. That was the question. Which limit, the lower or upper in the wavelength will give me the upper or lower limit in the frequency range. So when you place 400 nanometers, you will get 750 terahertz. And if you use 750 nanometers, you will get 400 nanometers. 400 terahertz. If you use 750 nanometers, you will get 400 terahertz as the frequency. Okay, so this is the range of the wavelength and the frequency of visible light. Now the human eye is sensitive to visible light. Actually, it is sensitive to wavelengths between 350 to 800 nanometers. So that is the range to which your eye can detect photons of this wavelengths. And it has a peak sensitivity. So it is most sensitive around 550 nanometers. So that is the wavelength of green light. So this graph is actually sensitivity of your of the human eye, and how it is sensitive to different wavelengths. So as I told, it's sensitive between 300 to around 800 nanometers in that wavelength range, and it has maximum sensitivity for the wavelength corresponding to green light, which is 550 nanometers.
Sir, maximum sensitivity at green light, what does it mean? What is the meaning?
Means yeah, so you can see on the left hand side it is actually written luminosity. It has not written sensitivity. So means like for every watt of light falling on a human eye, how many say photons it is detecting, or rather, so lumen is the unit of light. It's actually unit of so like what is the unit of power energy per unit time. So this lumen is also a unit of power. So it's also has the dimensions of watt.
Yes, a
actually.
small unit of power.
Yes. So do you know what is the equivalence relation between how many is
9.496 into 10 to the power minus.
okay? So 1
What?
lumen is 1.456.
49.
How much it is 6? Yeah. Watt. So that is a very 10 to the power minus 10. So roughly you can say 1.5 into 10 unit of power. And actually it is on not for any kind of energy, heat or other energy, but it's only used for light power in the form of light energy. So here
But
actually
how,
it is,
how human eyes can detect the photons, that is luminosity? How, like
yes,
a
so
green
that is what is actually kind of, so this is a measure of your sensitivity of the human eye. So basically what it
quantitatively
is
we
saying
can
is that
measure,
for every, hmm, sorry, I can't hear what you're saying.
sir, quantitatively, can we
Hmm.
measure the number of photons?
No. So this is what is this y-axis is telling you is for each watt of energy of a particular wavelength, how many lumens it is detecting. So that is what has been actually plotted on the y-axis. Means suppose if 1 watt of green light is falling on the human eye, it will detect about 650 lumens. Whereas if suppose the same 1 watt of blue light is falling on the human eye, it will detect 125 lumens. So if the same intensity of green, blue, orange, red, and yellow light fall on the human eye, it will show or it will appear to the human that green light is falling more or green light is more intense. So that is the sensitivity, meaning of sensitivity here. Means for the same, assuming that the same uh, power or same luminous intensity of light of various wavelengths are falling, it will it will give the appearance that the green light is the most intense, even though all the wavelengths are following in the same power or same intensity. Is it clear what I'm saying?
Yes, sir. Yes.
Yeah. So
Sir,
basically, if
sir,
the same, yeah,
is it mean we are observing most in green light, sir?
means this for the same energy of all the wavelengths are following on you. Suppose all the wavelengths are falling in with the same intensity. Means per unit area, the same amount of lumens is falling. Then even then, it will appear to you that the green light is more bright because your eye is converting more of the green light than the other lights. So that is the meaning of sensitivity of the human eye. Okay, is it clear now?
So our eyes is converted like this, na? So you are saying our eyes is converted. How green light is more, it will be fallen.
Yeah, so your eyes
So,
will
oh,
convert the different wavelengths, but it will convert more of the length around the green lights wave. Okay, so this means this is the kind of visible light and how the eyes respond to it. Okay, so this is a small exercise here. So you can find out like the wavelength of light which will be emitted if you make a LED of silicon, gallium arsenide, or say gallium arsenide phosphide. So gallium arsenide phosphide is a ternary semiconductor. Ternary means it has 3 elements, whereas gallium arsenide is a binary semiconductor. It's because it has 2 elements. Okay, so gallium arsenide in this gallium corresponds to which group in the periodic table? It's an arsenic to which group?
Fifth and seventh.
So gallium is third because it is
Third.
after the potassium or sorry, after the lithium. I mean, I think so. First, second, yeah, calcium group is there, and then the next group is gallium. So it is in the same, I think, as aluminum, right? Am I right or am I wrong about gallium being in the same group as aluminum?
Yes, sir.
So this is in the third group, and arsenic is in the fifth group. So so that's why this is known as a 3,4 semiconductor. Sorry, 3,5 semiconductor. Aluminum are in the group 4, so they are group 4 called 3,5 semiconductors. So you will come across that nomenclature sometime. So they are called 3,5 semiconductor because one element is from the third periodic group and one element is from the fifth group of the periodic table. And here you can see phosphorus is, I think, substituting in place of arsenic, and so you have a ternary semiconductor here. So as I said, for silicon, 1.1 electron volt will give you 1130 nanometers. So you can see that it is beyond, it's a larger wavelength than the red wavelength. So around 750 nanometers is the red wavelength. So it is larger than that. So this is in the infrared region. And if you put gallium arsenide, that also is in the infrared region, 869 nanometers, because so it will also be an infrared LED. But if you now use this gallium arsenide phosphide, it has a band gap of 1.9 electron volt. So that will give you a wavelength of 654 nanometers, which is in the center of the red zone. So that means it will give you a red LED. So you can see 654 will be somewhere in this range. So between orange and red, the center of the red zone. So you can use gallium arsenide phosphide as a red LED. So that is why there is a need for making such ternary semiconductors, because you can do band gap engineering, means you can engineer the band gap so that you get a band gap of particular choice, which will enable you to use it as that wavelength LED. So it is clear then that the wavelength frequency of light are directly related to the band gap of the material. And this gallium arsenide phosphide is just one example. There are many other such ternary and quaternary also. Means there are more than, three. There are 4 elements in the compound. So in a quaternary, there will be 4 elements, and with choice of band gaps, and so you can make LEDs of different lights or colors.
Sir,
So for
it is about the means frequency or wavelength of light. What about intensity? If we want higher intense light from LED, we expect a high intense light from one LED. Then what we have to do?
Yeah, so that actually is, you will see now that we will discuss now, that is dependent upon the current. So if you increase the current, the light intensity actually increases linearly, but then it will also saturate after some time. So if you have done experiment with LED, you will see that as you increase the current.
Sir, sometimes LED will means it is completely damaged by putting high voltage.
No, so you cannot exceed. So LED is, of course, a forward bias diode. So in any diode, if you remember the diode IV characteristic, what is the knee voltage?
The voltage after a diode conduct.
Yeah, so if you see a diode IV, you will see that it remains flat initially, and then suddenly it shoots up. So this is your I and this is your voltage. Actually, this is a ideal diode. Sorry, this is a practical diode. If you want an ideal diode, people model a practical diode with an ideal diode. So ideal diode LED characteristic will look like this. So it will not conduct till the knee voltage is reached, and as soon as the knee voltage is reached, it will give you infinite current. So that is the ideal diode characteristic. But in a practical diode, you get this kind of green curve. That is the current will actually start rising, and then you can say that it's almost becoming vertical after that. So after that point, the voltage across the diode, so if you have a diode like this in a circuit, the voltage across diode, so that is what has been plotted here, that does not change, but the current can drastically increase. So this is the knee voltage. That is, whenever you forward bias a diode, the voltage across the diode will not, Vd will always be less than equal to this knee voltage. But the current can rise as long as it does not damage the diode. So of course, there will be a maximum current which the diode can safely handle. So up to that point, the diode will work properly. And after that, if you exceed that current, then the power V into I will be exceeded. The safe value of power that the diode can handle will be exceeded, and your diode will be damaged. But below that maximum current, you can use this diode. And in that whole range of current from here, so from this value of current to this maximum value of current, your voltage will be near about Vk, that is the knee voltage. So it will not shift. So the voltage always remains almost constant at the knee voltage for any diode. So for LEDs also, they are diodes, so that will also be the case. But this knee voltage is specific for the material. So for silicon, as I said, it is 0.7 volts. For germanium, it may be 0.3 volts or 0.3 volts. And you can now see that the voltage, the knee voltage actually has been given for this different compounds. And also the color of this light which they emit, depending on the band gap, is also given. So you can see that we have seen gallium arsenide phosphide. Just last page, we have seen that it emits in the red region. So red and orange, you can see arsenide phosphide is there. Then gallium phosphide will give you green. Then if you put aluminium, indium, gallium phosphide, so that is a quaternary semiconductor, then it can give you yellow or amber. Amber is like yellow only. And if you now further go to gallium nitride, so gallium nitride gives you blue and white. And these are the forward voltages, typical forward voltages, which is basically the knee voltage. So you can see the knee voltage for blue and white LEDs are the largest, so around 4 to 5 volts. And for gallium arsenic phosphide, it is around 2 volts. In fact, for rest of them, it is around 2 volts. Only for the blue and white LEDs, it is between 4 to 5 volts. So generally, when we have a silicon diode in the equivalent circuit, when it is conducting, we assume that the voltage across this is 0.7 volts if it is a silicon diode. If in a question, if it is given to you that the diode is gallium arsenide, so what kind of voltage will you assume? So you will then, in that case, the knee voltage will be say 2 volts. And if it is say given to you, it is gallium nitride, or it is a blue or white LED, then the knee voltage will be around 4 to 5 volts. So that you can actually, you can remember that the knee voltage for blue and white LEDs is about 4 to 5 volts.
Sir, here all n gap, what is that mean, sir? All n gap?
That is aluminium, indium, gallium phosphide. Indium, you know, so that is indium. In is indium, and rest aluminium, you know,
Okay,
gallium,
okay,
you know,
sir.
phosphorus.
Okay, I am thinking.
Yeah, so this is a quaternary aluminium, indium, it is a quaternary semiconductor. think it is quaternary. Quarter from 4 and then NARY. So it is a quaternary semiconductor.
Sir, if this diode LED will be permanently damaged or only it will be stopped in particular time?
No, it will be damaged if you exceed its power rating. So every electronic
After
device
knee
has a
voltage,
power
after knee
rating.
voltage is
So every
permanently
electronic
damaged.
device has a power rating. It cannot. No, no, not after knee voltage. I didn't say it's knee voltage. Knee voltage you can operate in this range up to the current, the maximum current that it can withstand. You can go up to that range. So you can use up to here. After this, it will damage because you have exceeded the maximum current that it can allow it to pass through it. Or in other words, it is going to exceed V into I, the maximum voltage, V knee into I max. So that maximum power it will exceed, and then also it will be damaged because it has exceeded the maximum power that it can dissipate.
Its damage means permanently damaged.
Yes, if you exceed its current rating or power rating, then it is permanently damaged.
Okay, sir.
Yeah, so coming to that question, that how can we increase the intensity of light which has been emitted? We can control the wavelength of light by changing the material. But how do we calculate? Can control the intensity of emitted light? So that actually increases as you increase the forward current. So if you increase the voltage slightly, you can see that the current will shoot up. So your brightness of LED will also increase. But after some time, it will saturate. So that is actually it's shown in this two graphs here. So this is a graph of forward current and versus relative luminous intensity, means normalized at 10 milliampere. So what it has done is it has divided the luminous intensity at different currents by the value at 10 milliampere. So at 10 milliampere, it is 1. You can see at 10 milliampere, it is 1. Because all the luminous intensities have been divided by the value at 10 milliampere. So of course, at 10 milliampere, it is going to give you 1. Is it clear? Is it clear or not? I think it is not clear, right?
Yes, sir.
So this is relative luminous intensity. What is luminous intensity? What do you think? What is the unit?
Candela.
Candela, sir.
Okay. And what is lumen? What is the quantity it is representing? Mass, time, length, current, magnetic field? Huh?
Power.
Yeah, so 1 lumen is 1.496 maybe into 10 to the minus 10 watt. So from that you can remember that it is power. It's light power, you can say. But it is actually okay. So that's okay. But it is also a unit of, we don't call it light power. We also call it
Luminosity, sir.
luminous flux, or you can say, no, it is luminous flux. I'm not sure about luminosity. It is luminous flux. Okay, so basically that it's kind of confusing. Sometimes we consider flux as per unit area, but here actually it is lumen. It's a dimensions of power, you can remember, and it is a very small unit, 1.496 into 10 minus 10 watts, and is called the unit of luminous flux. And luminous intensity, as someone just now said, is candela. So what is the relation between one candela and one lumen? How many? First of all, they are not the same unit. So, but Okay, am I audible now?
Yes, sir.
Okay, so yes, so I was saying that 1 watt is related to 1 joule as 1 joule per 1 second. So similarly, there is a relation for 1 candela and 1 lumen. So do you know what is that relation? Anyone knows? Okay, so 1 candela, roughly, you know what is it equal to? It is the light. Sorry?
Sir, your screen is
Okay,
not
okay.
visible.
So 1 candela, you know what is 1 candela? Do you know the definition of 1 candela? Or not the definition, but like how it originated, or roughly equal to? So it is the luminous intensity. So 1 candela is the luminous intensity from,
Sir, we can define it like a power per unit solid angle, maybe.
yeah, so 1 candela is the luminous intensity which comes from 1 candle. So that is the rough estimate of the magnitude of 1 candela. And it is actually lumen per unit solid angle. So it is actually lumen per solid angle. So 1 steradian, right? So 1 candela is lumen per steradian, and so 1 candela is the total luminous intensity which is being emitted by 1 candle, and 1 candle is actually emitting in the whole in all directions, right? So that means it is emitting in a solid angle over a whole sphere. So what is the solid angle?
Four pi.
Yes, right. So a candle emits in a solid angle of 4 pi steradian, right? So 1 candela is being emitted in this 4 pi steradian. Okay, so 1 candela is actually equal to 1 lumen per steradian, all right? And so how many lumen is actually this candle emitting? So luminous flux of candle emitting 1 candela of luminous intensity. So what would be that? What would be the luminous flux of a candle emitting 1 candela of luminous intensity? So that means the candle is emitting 1 lumen per steradian, and that is being emitted in 4 pi steradians. So that is actually equal to 4 pi steradian into 1 candela, which is equal to 4 pi lumen. All right. So you can imagine that if there is a light source which is emitting 1 candela of light in a 4 pi solid angle, then the luminous flux of that source of light will be equal to 4 pi lumen. But anyway, so this equation or this equivalent relation is there. So 1 candela is equal to 1 lumen per steradian. All right, so now we are talking about relative luminous intensity here. So what is luminous intensity is now clear to you. Luminous intensity is like the light energy emitted per solid angle per unit time. You can think of it like that, right? It is 1 lumen per solid angle, means it is the power emitted per unit solid angle. So now this luminous intensity, we have added a word relative before that. So it is a relative luminous intensity, not absolute. So it is in units of the luminous intensity at 10 milliampere. That is what it has been written here. It is normalized at 10 milliampere. So what we do is we actually we have values of the luminous intensity for different currents, right? So we have for 5 ampere, 10, 15, 20. We plot them and we actually divide them by the value at 10. So if we divide the value at 10 by the same value, we get 1, right? So that is why you get 1 when you normalize the luminous intensity at different currents by the value at 10 milliampere. So that's why at 10 milliampere you get a relative luminous intensity of 1. So that is why you get 1 here. And you can see that the luminous intensity is increasing. So at 15 it is becoming twice that at 10. At 20 it has become almost thrice. So basically the luminous intensity or the light which is emitted per unit time per unit solid angle is increasing as you increase the current almost linearly. All right. But as I said that it will also saturate at some time. That is because the efficiency, that means the per unit electrical energy, how many light photons or how many light energy is being converted, how much electrical energy is being converted to light energy, that fraction will actually fall down as you increase the level of current. So after some time, because the relative efficiency is going down, so the brightness will saturate. So after so for you can see after 30 or 40 milliamperes, you can see that the relative efficiency is falling down. As a result, for each unit of electrical energy that you are giving, you will now get less units of optical energy. So that's why your brightness will saturate. So your LED will not become more and more bright as you keep on increasing the current, but it will flatten off at some value because this relative efficiency has decreased. Okay, so is this clear? Was I audible?
Yes, sir.
I was audible, no? Okay, so so that is basically that the light intensity from the LED will not increase continuously, but it will flatten off after some value of current. Now there is a quantity which actually quantifies this efficiency. That is, for every unit of electrical energy, how much light energy is being converted by the LED. So that is known as luminous efficiency. So that is the measure of the efficiency of a LED, means how well it is converting electrical energy to light energy. So what is this luminous efficiency? It is measured as lumen per watt, means for every watt of electrical energy, how many lumens of light energy it has emitted. Now for an HP red LED, so if you will look in the book by Boylested, so this is from the book by Boylested. So there they have mentioned the characteristics of a Hewlett-Packard red color LED, and that has been mentioned to have a luminous efficiency of 147 lumen per watt. That means for every 1 watt of electrical power, it is converting that to 147 units of a light power. Okay, so that is the meaning of luminous efficiency. And you have seen that lumen is a very small unit, 10 to the power minus 10 watts. So you can see that this actually is a very small fraction of the electrical energy. So you can see that how less out of a unit of watt, how less amount of that is converted into light energy. Okay, so luminous intensity is measured in lumen per steradian, that I have already told you, and it is equal to 1 candela. So I think I don't need to mention this. I've already discussed. Right, so this is the data sheet. So you know, yes.
Can you once again tell me that 147 lumen per watt? So what is
That is the
physical meaning,
value
sir?
actually of this red LED from Hewlett Packard. Okay. So this is given in the book by Boyleston. You can look at it, and this chart also is showing that only. So you can see here in this chart, it is luminous efficiency or efficacy is given as 147 lumen per watt. So for every watt of electrical power that is given by the battery to the LED, it is converting for every watt of that power 147 lumen of light power, right? So if you're giving 1 watt of electrical energy, it is converting 147 into 1.496 into 10^-10 watts of light per unit time. That is what it is doing.
Okay.
And this is actually an example of data sheet. So every electronic device has a data sheet or data specifications. Nowadays you buy smartphones and you on laptops and you see what are the specifications like RAM and memory and so on and so forth. So similarly, every electronic device has a data sheet, and it can be looked up in the internet as well for the model number. So for example, this HP red LED has all this in the data sheet. So it's absolute maximum ratings at 25 degrees Celsius. And it also says derate by for every 50 degree by 0.2 millivolt per degree Celsius. So the things will change if you rise the temperature by say 50 degrees. So it will change at a rate of 0.2 millivolts per Celsius, whatever is written here. Now, you just now said what will happen if you increase the current to a large value. So you cannot exceed the 60 milliamperes. If you exceed the 60 milliamperes at knee voltage, then you will burn it. So that is the peak forward current that it can withstand, and it can operate in between this temperature range. And this is also the maximum power. So around I think it's 2 volts is the knee voltage. So you can also calculate from this actually, because maximum power will be knee voltage into maximum current. So maximum current is 60 into 2 gives you 120. So most probably 2 volts is the knee voltage for this red LED from Hewlett Packard. There are further more specifications. So this is luminous intensity, again measured in candela. So it is so it is millicandela. So it is typically it will give you 3 millicandela. That is 3 millilumen per steradian. So that will be the luminous intensity of the LED. And it is actual luminous intensity, means it is not in all directions, it is going in a particular direction, and that direction is along the axis. So the LEDs are designed that it emits most of the light along the axis of the LED. So that's why this is axial luminous intensity, and it comes to 3 millicandela. And the peak wavelength, as you can see, this is a red LED, so it is around 635 nanometers. And dominant wavelength is also nearby about that. Forward voltage, see, we just now were thinking what was that, plus 2.2 volts. So that is the knee voltage. So this is the knee voltage of this diode. Okay, so now we come to red LEDs and green and blue, sorry, red, yellow, green LEDs were there for a long time. Okay, but only recently this white LEDs has been used in illumination. So you are now only seeing in home lighting and street lighting, etc. On cars and automobiles, you are using white LEDs. But why do you think is it a recent phenomenon? Because LEDs have been there for some time now.
Hello. Hello, sir.
Why do you think it is a recent phenomenon? Or you do not agree that it is a recent phenomenon? Okay, so this is a chart. This is from Banerjee and Streetman, not in Boyle Street. So this is the improvement of luminous intensity of LEDs over time. Okay, so how the luminous intensity of LEDs has changed as time has progressed. So you can see in 71, there was gallium arsenide phosphide, means 0.6 arsenic and 0.4 phosphor. That is the ratio of this alloy. And that gives you red color. But its lumen per watt was, so this is the efficiency, you can say, luminous efficiency. It was less. How much was it, do you think it is? What is the value here? What will be the value? This value, how much will it be?
Nearly 0.1.
Sorry, I cannot hear you.
Hello?
So
nearly 0.1 now.
0.2 actually, right? Between 0.1 and 0.2, something right there. Okay. And what about this gallium, phosphorus, and then zinc and oxygen is doped, I think, there. That will be 0.2, 0.3, 0.4. So this is around 0.4 lumens per watt. So you can see that as time has progressed, better efficiency has been achieved. So in like aluminum, gallium arsenide, red LED, you could achieve up to 2 lumens per watt. So that was achieved in 1985. And then again in allium, indium, gallium phosphide, you could achieve up to 10 lumens per watt. But this is the incandescent lamp. So what is the incandescent lamp? What do you think is the incandescent lamp? What do you think? What is the meaning of this incandescent lamp?
40-watt bulb.
40-watt bulb.
So we can imagine a burner, Bunsen burner.
No. Somebody said 40-watt bulb. So is the watt fixed? Did you say 40 watt or what did you say? I didn't hear properly.
So normal bulb we use in our like.
Yeah. So wattage is not fixed. What can be 1 watt, 2 watt, 5 watt, 0 watt also. Yeah. So incandescent lamp is the Edison lamp. So you know about Edison, right? So this is the filament there, and you have a bulb inside, right? I mean, the bulb is there, and you have a filament, tungsten filament, which is heated and it emits light. So the incandescent lamp had a luminous efficiency of 20 lumens per watt. So unless your LEDs could cross that, there was no point in replacing incandescent lamp with any of these LEDs. And moreover, till 2000, you can see that, I mean, till 95, you can see that only blue color came for the first time. Before that, there was no blue color. And for white LEDs, so we cannot use green, red, or orange as our light for illumination. So that was also one reason that blue LEDs were discovered quite late. But also the other reason was that their luminous efficiency was below incandescent lamp and also below fluorescent lamp. So fluorescent lamp is like 10, so this is 10, 20, 30, 40, 50, 60. So probably 60 lumens per watt was the luminous efficiency of fluorescent lamp. So only LEDs increased beyond was still below that of incandescent lamp and fluorescent lamp. So there was no point, because we'll end up using more electrical energy if we are going to use any of these LEDs, right? So one was that there was no blue LED, and the other was that they were converting even less to light energy as compared to incandescent and fluorescent lamp. Only when the blue LED was discovered and the LED luminous efficiency has increased beyond that of fluorescent lamp, now you can use it. So there are two ways of obtaining a white LED. One is you combine a red LED, a blue LED, and a green LED together. So you know the primary colors are red, blue, and green, and if you combine them, you get white light. So that was one. But the most common nowadays is you use only a blue LED and you use some phosphors. So phosphors are materials which show phosphorance. Means if you shine light on it, like if you make blue light incident on some larger wavelengths, like it can now emit in yellow, green, or yellow and red. So what will happen is when you have a blue LED with a phosphor, the blue light will excite the phosphor and the phosphor will emit green and yellow or green and red light. So now this green and red light from phosphor and the blue LED light together will give you the appearance of white light. So red and green from phosphor will give you the appearance of white light. So that is the so out of these two options, now the second option is being more widely used, and their luminous efficiency has also gone up from fluorescent lamps. So now for less amount of electrical energy, you can get the same amount of light which is used to come from fluorescent lamps. So that is why you are now seeing that LEDs, white LEDs are replacing illumination in houses and streets and also in automobiles. Okay, so any question here?
Sir, is there any lifetime of LED?
Yeah, so lifetime is also better. It's about quite large, about 20,000 hours and so on. So that way also it has more lifetime compared to luminous, compared to this fluorescent and incandescent.
Sir, but lifetime depends on which thing?
Well, that is maybe, so for example, tungsten, we know that because of regular heating, it kind of gets destroyed, right? But here the mechanism is not Joule heating, right? So those things will matter. So exactly what parameter gives the longer lifetime of LEDs, that I'm not sure right now, but yeah, they have a longer lifetime.
Sometimes LEDs are also heating due to the emission of phono.
Yes, so of course, as I said, only certain like 147 lumen per watt is being converted to light. The rest is converted to heat energy. So there is going to be heat energy.
Due to that heat, maybe lifetime, it will depend to that heat energy.
Yeah, lifetime can depend on that also. Okay, so any other question in this? So that is what I said. White LEDs are obtained by using blue LED and phosphor. When blue light hits the phosphor, it emits yellow and green light, which together with blue light gives the sensation of white light. Okay, so there is one question here, which I made myself here. So what is the luminous efficiency of a fluorescent tube light? I think that I've already answered. So what is the fluorescent lamp's luminous efficiency? You can read it from this graph. It is already written there. I wrote it down. 60, yeah. So roughly 60 lumen per watt. So now, if a white LED emits the same amount of light as a 40 watt fluorescent tube light, and has a luminous efficiency of 200 lumens per watt, what will be its power requirement? So that is the question. So LED is emitting the same amount of light as a 40-watt fluorescent tube light, and it has a luminous efficiency of 200 lumens per watt. So the question is, what will be the power rating of the LED? So tell me if this is solvable. So what will be the light emitted by a 40-watt fluorescent tube light?
Sir, voice is not clear.
So for a 40-watt fluorescent tube light, what will be the luminous intensity, luminous flux? Is it clear now?
Yes, sir.
So a tube light has a luminous efficiency of 60 lumens per watt, and the power of the tube light is 40 watts. So what will be the light that will be 2400 lumen? Is this clear?
Yes, sir.
So the question is, LED is emitting that same amount of light. So for a LED which will emit 2400 lumen, what will be its power? What will be the electrical power that you need to feed to this LED, given that its efficiency is 200 lumen per watt? So now I think you can do this.
12 watt. 12 watt. 12 watt.
12 watt. Okay. Yeah. So for every watt it is producing 200. So for producing 2400, it will be about 12 watts. Correct. So that should be the power of LED. So basically that means if we have an imaginary LED of this much efficiency, then it can produce the same luminous intensity or luminous flux as a 40-watt fluorescent tube light. Okay, so that was the question. All right. I think that's all for today's class. Okay, so if no questions, then we can stop here. All right then.